Here begins the lesson on the Arrhenius equation dealing with temperature and how it affects the kinetics of a reaction, the rate in which reactants turn to products. We need our notepacks out, we need our equation page, and we'll need a calculator. The equation page is on the back side, dealing with temperature versus K constants, known as the Arrhenius side. The Arrhenius equation is on the same side as how to generate instantaneous rates. Just to clarify where we're looking. We begin discussing temperature and how it affects the collisions of molecules. We see from the picture on the slide, these are little glow sticks, and on the left of that picture where we have warm water, the glow stick, which has a chemical of phospholumescent, it's glowing quite brightly. And in lower temperatures, where it's cooler, lower kinetic energy to those molecules, that glow stick is much dimmer. The graph showing the K constant, and this is the lower graph, versus temperature in degrees Celsius, shows an exponential rise. As we warm up molecules, the K constants also rise exponentially. Generally speaking, the rates of most chemical reactions increase as the temperature rises. And as the temperature rises, so does the reaction rate. This is because K, the rate law constant, is temperature dependent. Remember, so far in all of our calculations, we've made sure to say temperature remains constant. When we run the initial rate law, running data trial after data trial, generating rates from instantaneous methods, we always hold temperature constant. Now we'd like to vary the temperature, generate a variety of K constants, and determine what's called the activation energy of a formula. The activation energy, that little energy barrier that's got to be input of energy in order to get reactants to turn to products. And it all begins with an explanation of our collision theory. The collision model speaks of chemical reactions where bonds are breaking, atoms are rearranging themselves to form new products. In order for reactions to occur, molecules must physically collide, and they must collide with enough energy and with the exact spatial orientation for a successful collision for a reaction to occur. The greater the number of collisions occurring per second, the more likely the rate would be to increase. Greater collisions mean a likelier odds of a successful orientation. Now look very carefully at this picture and see what we're noticing. The collision model, and I'm just going to speak in general terms. Before the collision, take a close look. We have an atom, I'll call it green atom, colliding with a molecule. It goes green, blue, red. So three different atoms bonded to make a molecule. In the middle we have a collision, and boy does that collision hit smack on to the green molecule. If that green molecule were to hit at any other point, on the side of the green molecule, perhaps even on the blue side or the red side, that's an unsuccessful spatial orientation. Only if we have the correct orientation where the green smacks right onto the green with enough energy will that bond break and a new bond form. The orientation factor is critical in a successful collision. The orientation and the energy both play a key role in the number of successful collisions as reactants turn to products. That orientation factor is simply described as when molecules are orientated in a three-dimensional space and must align themselves in a very particular order for a successful reaction to occur. Atoms must be suitably positioned for bonds to break and for new bonds to form. They must have a head-on collision with the atom they're trying to connect to, so much so that they break the bond and form a new bond. Orientation and activation energy play a huge role in the number of successful reactant molecules turning to products. So to review, we've said molecules must collide to react, and that temperature affects the rates simply because collisions are more likely. We understand that from our very first experiment. You increase the kinetic energy when you warm molecules up. Therefore, if they have more kinetic energy, more energy of motion, they'll hit with a greater force. That force that must be provided is key in a successful reaction. We have a term called activation energy, that minimum amount of energy that must be given to a reaction to get it going. Reactions that are spontaneous require an activation energy, a little barrier standing between reactants and products. In a simplistic form, this is an example. We have a golfer standing between a little putt here, and unfortunately she's got to get over this hill before the ball will go into the hole. That hill represents an energy barrier. Suppose she, the girl, represents reactants, and the hole represents the products. What stands in the way between the two is not a flat line reaction grid at all, but a minimum amount of energy required to break a bond has to be input. If she puts hard enough, she can overcome that energy barrier and have the ball go over the hill. Unfortunately, if the energy level's too low, the ball will roll right back, and she's right back to where she started from, adding a stroke to her scorecard. So just as a ball cannot get over a hill if it doesn't have enough energy to roll up, a reaction that doesn't have enough energy, enough to overcome the activation energy barrier, will go nowhere. The activation energy is defined as that minimum amount of energy necessary to make a reaction happen. I believe we flip our page in our notes here and we see a grid, a reaction coordinate diagram. The next couple of slides diagram reactants turning to products. And I'm asking that you just take your time and sketch this very, very important grid into your notes. It'll help you analyze the components of the grid as you create them. Notice on the y-axis we have potential energy. Potential energy in chemistry is the energy that's stored in a chemical bond between atoms in a same molecule. They're little storage tanks of energy, usually measured in kilojoules. On the y-axis, you can think of that as the pathway, or sometimes I just simply write time. As time goes by, reactants turn to products. Notice the reactant is CH3 N triple bond C. N triple bond C is the reaction pathway. As the energy begins to rise, we've got some labels to pull in. Notice at the beginning where the reactant is, to the very top of the energy hill, please label that as E sub A. The activation energy is defined as the starting point of the reactants to the very tippy top of the hill. Now on the product side, notice we've got just a simple rearrangement here. CH3C triple bond N. This reaction was a rearrangement of the same molecule. The product is of lower energy than the original reactant. Shaded yellow is a delta E, the change in energy from the overall equation. The correct vocabulary word for that would be enthalpy, delta H. The enthalpy of this reaction is overall exothermic, where reactants turn to products of a lower energy. The delta E would be the value we record in our thermochemical equation. At the very top of our hill, we have what's called an activated complex. Think of that in terms of just this moment in time where a correct collision and spatial orientation have occurred with enough energy where bonds are breaking and new bonds are forming, being represented by dashed lines. That dashed line is representing that moment in time where bonds break and new bonds form. A reaction coordinate diagram like this for the simple rearrangement of methyl isonitrile. Reactants turn to products. It shows the energy of the reactants and products overall, exothermic. The delta E here showed a net loss of energy from reactants to products. Notice at the very high point of our diagram, we have something called the transition state. That's where the dashed lines are. I call it the activated complex. Some texts call it the transition state. It's that arrangement of atoms at the very top of the energy barrier where bonds are breaking and new bonds are forming. Reactants turn to products, and at that moment in time where they meet the top of the hill of the activation barrier, they call that the activated complex. Kind of that between species of reactant to product. The activated complex does not exist long. It's only at the top of the hill that separates the reactants from the products, known as the activation energy barrier. Of course, we understand the higher that mountain we have to climb, the slower the reaction. The lower that hill, the quicker the reaction. And there are things we can do to manipulate the activation energy of a reaction. And that's the whole story coming about a catalyst. A catalyst will provide an alternate pathway for a reaction mechanism, an alternate pathway with a much lower activation energy barrier. The higher the activation energy, the slower the reaction. Not as many molecules meet that criteria of the minimum amount of energy necessary. We now begin to explore Arrhenius and his influence on the world of chemistry in terms not only of acids and bases, of which he is the icon, but also in terms of the Arrhenius equation in the kinetics chapter. He studied very carefully how temperature affects the number of successful collisions. We might think, generally speaking, warming up a temperature, warming up a kinetic energy of those molecules, making them move faster, definitely influences the rate. But how? We'll soon discover it's not a direct relationship, but more of an exponential relationship. The number of successful collisions that are necessary just by warming up the molecule rises drastically with each degree we give it. F in the Arrhenius equation stands for the fraction of molecules meeting the minimum criteria to make it over the energy barrier. That is equal to E. Now E is called Euler's number. I know that sounds different than what it looks like for spelling. It's simply a man's name. It's the opposite of a natural log. Look at your calculator. Find the ln key, sits right below your log, log. The natural log has a different base than log, which is base 10. The natural log is a different base on Euler's number. If you look above your ln key, see the e raised to the x? That's Euler's number. E is the opposite of natural log. If you press E on your calculator, second function ln, you'll literally see E raised with a little caret key and a parenthesis come up. We type in negative EA over RT, close the parenthesis, equal, and that will tell us the number of molecules, the fraction of the number of molecules that meet the minimum criteria of energy to make it over that activation energy barrier. E is Euler's number. EA stands for the activation energy. Notice in our equation it has a negative sign there, and that's on purpose because without it we would get a negative activation energy, which absolutely makes no sense since it's a barrier. It's a mountain we must climb. It's not a dip or a valley. It's a mountain we have to get over. Activation energy is always a positive number in joules. Activation energy measured in joules. R is the ideal gas constant from our old PUV-NERT days, or even pi equal MERT from the osmotic pressure of colligative properties. The units on R is critical. It's joules, oh that's misspelled, I'm sorry, Joules, joules per Kelvin mole. I say that because when we place in activation energy, it must be in a joule to match the R constant 8.31 unit joules per Kelvin mole. And temperature, of course, must be in the absolute scale, 273 plus Celsius. We can calculate the magnitude of F, F standing for the fraction of molecules that meets or exceeds the minimum amount of energy required to form products. How many molecules have a successful collision to make it over the energy barrier? Now grab your calculator. Let's try one where it says suppose. Suppose we have an activation energy that's 100 kJs per mole, and that's quite a typical value for most reactions, 100,000 joules. The temperature is 300 Kelvin, which is about room temperature. It's 27 degrees Celsius. That's a little bit warm for room temperature, but 300 is a nice even number. I'd like us to calculate the value of the fraction of the molecules that has the energy equal to or greater than EA. Plug and chug. We're going to hit on our calculator the following, and I do want you to hit with me to verify the answer. Please don't wait until test day to make your calculator your friend. We're calculating for F, the fraction of molecules that meet the criteria for the energy barrier. We hit second function, natural log. That's Euler's number. Now on your calculator screen, it should say E with a caret key and an open parenthesis. Type in negative 100,000 joules. The problem gave us 100 kJs, but we must match joules in the 8.31 and joules in the activation energy. The negative sign is there on purpose to make sure activation energy comes out as a positive value. It's an energy barrier. It's a positive number. Negative 100,000 divided by, parenthesis, 8.31 times 300, close parenthesis, twice. Press equal. Your screen, 3.79 times 10 to the negative 18. Now this is a number. There's no units. It's a number. It's telling us a fraction of molecules that meet the criteria. So, what might that mean? What does that number mean? Well, a number by itself doesn't mean much to us. We have to compare it to another scenario. Let's suppose same equation, but we warm it up 10 degrees. I'd like to now know the influence of warming up 10 degrees on the fraction of molecules meeting that minimum criteria. Let's re-hit. Instead of using 300 Kelvin, let's put in 310 Kelvin. Hit it with me. Do not wait until test day to make the calculator your friend. Hit second function ln. On your calculator, you'll see E raised to the open parenthesis. Type in negative 100,000 joules. Divide by parenthesis 8.31 times 310. Close parenthesis twice, equal. We get a number. That number has no unit. It's a fraction. But now what is interesting is comparing the two numbers. Let's place the larger over the smaller and see what we find. I have a mistake on the slide I'm seeing right away. Please fix this with me. It says when we compare the number of molecules having successful collisions, the answer the first time, 1.38 E negative 17, but we divide that by the answer from 300 Kelvin, 3.79 E negative 18. I have a mistake on the slide. Please adjust accordingly. 1.38 E negative 17. That was our answer at 310 Kelvin. Bigger number. Divided by 3.79 E negative 18, the answer to our first at 300 Kelvin, we get this ratio of 3.6. The 10-degree increase in temperature produces almost a 3.7-fold increase in the number of molecules meeting the minimum energy. It's almost going 4 times faster by warming it up 10 degrees. So Arrhenius explored how the number of molecules meeting the criteria exponentially influenced the reaction rate. Not a straight line graph, but an integrated graph using exponents. The more he studied, the more he focused on 3 specific factors He found that reaction rates obeyed equations based on those three factors. The F, what we just calculated, the fraction of molecules possessing an energy equal to or greater than EA, standing for activation energy, always positive. The number of successful collisions occurring per second, and those that actually have the correct or appropriate spatial orientation. Those three factors greatly influence the rate of our equation. And he incorporated into an equation, quite famous, the Arrhenius Equation. AP Chemistry, on the test, the Arrhenius Equation quite often appears. Just saying. Those three factors, savante Arrhenius, same famous chemist who gave us acids start with an H, bases end with an OH. He developed the following mathematical equation between K, the rate constant, and the activation energy. You know that when you warm up an equation, it takes off. K is equal to A times E raised to the power of negative EA over RT. Remember it. What do those letters mean? Well, K is the rate constant. Rate is equal to K times the concentration of reactant A raised to some power times the concentration of B raised to some power. Those powers are called orders. K is a rate constant. It is experimentally determined at a constant temperature by manipulating initial rate data. But if you warm it up, we get a different K. You cool it down, you get a different K. Running the same equation over and over, varying the temperature, allows us to get a variety of K constants. EA is the activation energy. Remember to make sure you plug that in with joules of energy to match the R constant, 8.31 joules per Kelvin mole. Kelvin is a man's name as well, just as Joule, just as Arrhenius, it should be capitalized. T is the Kelvin temperature, and the y-intercept will end up being our frequency factor. The number represents the likelihood that collisions would occur with the proper orientation in space. Dead-on collision with enough energy to break a bond and form a new bond. The Arrhenius equation. Differentiate and integrate, those two terms from calculus, are tools to a chemist. Not necessarily does it meet our criteria for understanding just yet. Depends on where you are in your math journey. But if I wanted to turn the equation we just wrote into a straight line equation, we end up taking the integral. Now remember, the Arrhenius equation, K is equal to AE raised to the power of EA over RT. If I just want to integrate that to create a straight line, we start by taking the natural log of both sides of our equation. If we take the natural log of both sides, we find ln K is equal to EA parenthesis 1 over RT plus the natural log of A, the frequency factor. Notice it's a straight line. Y equal mx plus b. We can use our lists, list 1, list 2 in our calculators, and let this do the work for us. List 1, the reciprocal of Kelvin temperature. List 2, the natural log of K constants. Find the best straight line. So you take the linear regression of list 1, list 2. Find y equal mx plus b. Activation energy for the slope of the line is negative EA over R. I'm going to say that again. It's on your equation page. Write it into your notes. Take the graph from the previous slide, I'll try to show it again, which matches the graph that I hand-drawn on your equation page, and I want you to draw it into your notes. Draw a straight line where natural log of K is on the Y, the reciprocal of the Kelvin temperature is on the X. We get a straight line where the slope is equal to negative EA over R. EA will be in joules. R is the gas constant, 8.31 joules per Kelvin mole. This straight line equation allows our calculator to predict the activation energy, where that's the slope of the line set over R. The natural log of K versus the reciprocal of the Kelvin temperature gives us a straight line, y equal ax plus b. I'm just asking you to draw that into your notes to help you become familiar with the graphical form of the Arrhenius equation. One last thing to jot down before we start our first practice problem. Sometimes it's easier to use a non-graphing form of the Arrhenius equation. If I'm given a list of temperatures versus K constants, and if you peek ahead a little bit down further at a practice problem right here on our notepad page, I can see temperatures in degrees Celsius given to us in a list, and K constants in per seconds must mean it's a first order reaction. If it's a per second, I'm looking at a list of K constants. If I'm given a list, I can either use list 1, reciprocal Kelvin temperatures, list 2, the natural log of Ks, graph it, find the best straight line, take the negative slope, EA over R. Very easy to do in our lists of our calculator. But here's an alternate. It's a non-graphical way to calculate the activation energy. Write this into your notes. The natural log, parenthesis, K1 set over K2 is equal to, notice here it's positive, positive EA over R, both must be in joules, EA over R times, parenthesis, the reciprocal of Kelvin temperature 2 minus Kelvin temperature 1. Reciprocal of T2 minus reciprocal T1. If we're going to do a non-graphical form of the Arrhenius equation, I highly recommend you take points from the list that are as far apart from each other as possible to get a best representation of the line. Do not pick points that are right next to each other, or you have a very short line you're trying to find a slope for. Pick the first point in the list, pick the last point in the list. That gives you the best representation of that line. So let's pause here. We're ready to do a practice problem that will take place in the next video. Have your calculator ready to hit with me.